On any of the kinds of process problems that you might encounter.
Oh, when I did it, my
But in order to actually do it, I wonder if I can get going. To actually do it, we need to concern ourselves with the properties of the actual materials that are going to be undergoing these processes. So that's where I'm going to start today. So this is our second unit, looking at the properties of pure simple compressible substances. So notice a couple things about that. First of all, I said we're going to restrict ourselves for the moment to pure materials. We'll later on go to mixtures. And they're simple compressible substances. Now we all know what that is. Those are materials subject to PV work only. And the important thing we know about that, that's a simple system, so we know that the state postulate tells us that we need to specify only two independent properties to fix the state of a system like this. Now, just to make a notice to you, I've already posted this, but reading suggested here would be pages 232, 249, starting in chapter 4. Now, we right away need to make a distinction between measurable properties and abstract properties of these kinds of materials. And it turns out that the list of things that we can actually measure in the lab is pretty short. But we want to look at that first. What can we actually measure in the lab? And then after we've got that nailed down and understand it fairly clearly, then we can see how we can use those measurable data to actually calculate values for the abstract properties in terms of which we actually solve problems. So that's the strategy here. So let's look at the properties that we can in fact measure. And as it says, it's a fairly short list. We can measure volumetric properties, and by that we mean the PVT equation of state for the substance. We can measure phase equilibrium curves, that is, we can measure vapor pressure curves, melting point curves, sublimation pressure curves, and the like. So those are fairly readily obtainable in the lab. And we can do calorimetric measurements. We can measure the heat capacities. Normally that's either a heat capacity at constant volume or constant pressure, but it can be something else as well. And we can measure heats of phase change. This is the liquid vapor phase change, or it could be the heat of melting. Could be other phase changes. And we can measure heats of reaction. So that constitutes the calorimetric properties that we can measure in the lab. And then if we are dealing with multi-component systems, we can measure their composition, but we're going to, for the moment here, stick to pure components. So that's the list. There's really nothing more than that that we can actually measure in the lab. So our goal now is to go from that set of things that we can measure in the lab here to calculate abstract properties. Things like here, delta H, delta U, delta S, delta G. These are the things in terms of which we can normally solve problems. We're also going to be interested in a number of abstract thermodynamic derivatives. For example, here's a couple of them, but there's many others that we can be interested in as well. Just for the heck of it, do you happen to know what that is? That got a name for you? I'm just curious what you learned in 325.
Sorry, could you repeat the question? I was trying to get it all written
Say again?
down. Can you repeat the question? I was trying to get it all written on my paper.
How about this derivative? It's just I'm just asking it rhetorically because I'm curious.
Oh, partial derivative of temperature with respect to pressure.
The Joule-Thomson coefficient. We'll see it later. But I was just curious to know if you had seen it. So that's the setup here that we want to go through. So our first job is to be looking at these measurable properties. The first thing that we have to say before I even get into that is that as soon as I fix the pressure and temperature, I fix the state of the system. But that state can be at least one of three different or more phases. In other words, there are phase states, solid, liquid, gas, in which the system might find itself. There's at least that for every material that we can call a simple compressible substance. But we may have more, and we often do have more than a single solid phase state, referred to as allotropes. So that's the first thing we're concerned ourselves with, is the phase states, and we're generally interested in the region of behavior in which all three of them actually exist. So this is just a generic diagram, phase diagram on pressure and temperature coordinates to represent the behavior of one of the simple compressible systems that we might be interested in describing. So if I pick a pressure and a temperature, here's a pressure and a temperature, that should uniquely define the state that I want to describe, and that turns out to be a liquid in this case. If I pick another set of pressure and temperature values, I'm going to get something else. For example, I might end up in the solid phase state, or of course I might end up in the gas phase state, indicated here. But interestingly, I might also land on one of these phase boundary lines. So what this is the vapor pressure curve, right? This would be the melting point curve, and this is the sublimation pressure curve. Those are all our phase equilibrium lines, and the phase state that we end up in might actually be on one of those lines, which would be of interest, and we'll focus quite a bit of attention on it later on through this lecture. It's particularly interesting here is the triple point where all three phases coexist together in a state of equilibrium. And so every simple compressible substance that we might deal with has a triple point. And you might find some tabulations of those, although they're rather scarce. But let's look at a few of them so we can get an idea of the nature of this triple point. It's a fairly easy thing to measure in the lab. So here are some triple point data for gases, liquids, solids. And here's the triple point temperature for them and triple point pressure. So let's look at them one at a time. The triple point temperature is interesting, but what we notice is that it's almost exactly within 1/10 of a degree or so of the atmospheric pressure melting point. And that's going to be true kind of across the board. So that's what the triple point temperature looks like. The triple point pressure is pretty low. Let's remember that, I can write it here, 1 bar is equal to, it's a little bit hard to write with this thing, 100 kilopascals. So these are all really quite low pressures, just a few kilopascals. And a bar is about an atmosphere, so a little bit less than an atmosphere. With one exception, look at this one. Carbon dioxide has a triple point pressure here. It looks like it's going to be a little more than about 5 atmospheres, which means that its behavior has some unique features, which is worth looking at here for a second on its phase diagram. So here's the pressure temperature phase diagram for carbon dioxide, and it looks similar qualitatively to what I've shown you for the general case, but let's consider that we have carbon dioxide gas at room conditions, and here I've indicated it. And then we cool that gas down. So if we do that, we don't go through a liquid state at first like we would for ordinary gas. We cool it down, 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 and then it liquefies, and then at a lower temperature it solidifies. But for carbon dioxide, because we have a triple point pressure, which is higher than atmospheric pressure, it goes directly to the solid state, something that we know of as dry ice. And this is, I don't think it's unique, but it's very rare to find another substance. And I looked quickly, was not able to find another example for it, but I think they probably exist. But like I say, it's very rare. The triple point pressures are usually quite low. So let's consider the other end of the vapor-liquid equilibrium curve, namely the critical point. The critical point is the end of the vapor-liquid equilibrium curve, beyond which we don't have any distinction between liquid and vapor phases. And so what that means is that, and here I'm just labeling them here as critical point temperature, critical point pressure. It means that beyond the critical point in terms of temperature or pressure, we're in a region we just refer to as the supercritical region. It's not a phase state like these others, but it's a region that we can define as being above the critical point temperature and pressure. This varies quite a bit from one substance to another, so unlike the triple point, it's a pretty good fingerprint representing the behavior of the materials, and we'll see later as we get into it how we can make use of that critical point to do a lot of things. We have data tabulated for this critical point in your Appendix A of the book. So here they are, critical point temperature, critical point pressure, and the book lists these properties for about 100 or more different substances that you have at that point. unfortunate that they don't also list the critical point volume, but that is available in the literature as well, so it can be found. And if it looks like we need it, I'll supply you with a set of critical point data that includes the critical point volume. So let's ask the question of what about this one? I've got it just hanging there. If I chase that up, that is the melting point curve, am I going to get another critical point for the solid liquid? Well, we have to go to quite a bit higher pressures in order to explore that. So to look at it, let's look at some data for water at very high pressures. Now, the first thing to notice is that the region of the previous graph is confined down here below about 100 atmospheres, and you can see here we're going up to several thousand atmospheres of pressure. And so if we chase the curve up, what we find is that we get not another critical point, but we get another triple point, because we have different solid allotropic phase states for water. Here it goes into triple point with the ice 3. And here are other types of ice, different allotropic forms for ice. This is a rather old diagram, so the picture is a little bit different now. You'll notice that, for one thing, ice 4 seems to be missing. It was proposed in earlier data and then found out that wasn't the case, so that's just been removed. But other types of ice have been identified as well. What about ice 9? Anybody heard about ice 9? What about that? You read Kurt Vonnegut's Cat's Cradle. Ice 9 is a fictitious form of ice which actually exists in the solid form at room temperature. Very dangerous because if a little bit of it gets into the ocean, it will all freeze. So we're not going to find that on this diagram. But interestingly enough, if you look at recent data, there is an ice 9 right now, but not the one that Vonnegut proposed. So that's the answer to that. We have only one critical point. So if I say critical point, I don't even need to say vapor liquid critical point, because that's the only one that there is. Excuse me.
Yeah. How much of it will freeze? Like, if it drops into the ocean?
No, that's fake. So don't. That's Vonnegut's
Oh, you were
fictitious
Oh, okay.
speculation, but I was curious to know if anyone was aware of that.
Gotcha.
Let's focus some more attention now on these phase boundary lines. They're going to be very interested in that. And what they are pressure-temperature relationships along these equilibrium lines. So we would like to know, how does pressure vary with temperature, say along this line? That would be what we know as the vapor pressure curve. This would be the melting point curve. This would be the sublimation pressure curve. So we'd like to know how to describe those mathematically. Now, it turns out that we can derive rigorously a relationship in the form of a differential equation that gives us the equation for each of these lines. And that's the Clapyeron equation. Now, as we get further into the class, I'm going to derive this rigorously, but for now, just let's take it. So we'll see that the pressure-temperature derivative along any one of these lines is equal to the heat of the phase transformation. These are all first-order phase transformations, so this is the heat of, for example, the heat of vaporization for this curve, divided by the temperature times the volume change, molar volume change, when we go from one phase to the next. So everyone see that? And this is rigorous, so if we have data that allow us to evaluate it, we can nail it in exactly. It can be used to describe all three of these curves, and the appropriate quantities here have to be used in each case. So we can use the Clapyeron equation to describe vapor pressure curve, melting point curve, and the sublimation point pressure curve. So let's explore this a little bit further. This would be the vapor pressure curve, again rewritten, the Clapyeron equation. But it turns out that it's convenient often for situations if we're in the phase state for which this is valid, which is often the case, to make a couple of approximations that make it easier to integrate this so we actually get an algebraic equation for the vapor pressure as a function of temperature. If we assume that the liquid molar volume is much less than the vapor molar volume, such that we can neglect this, and if we assume the vapor is effectively an ideal gas, then this quantity, the volume change, can be approximated as RT over the pressure. So if I stick this in for delta V, suggest that here. Then it converts the equation over into a form which is easier to deal with. So that turns into the differential equation again, but it's an approximation because it involves these two ideas. And we call that one the Clausius-Clapyeron equation. And it's a reasonable approximation if we're not too close to the critical point. So if we get up to a point of TR stands for the reduced temperature, that's temperature divided by the critical temperature. And if that's less than about 0.7, just as an approximation, usually the Clausius-Clapyeron equation is good enough. Now we can use it to describe the sublimation point pressure curve as well. Same form here. It's the Clausius-Clapyeron equation now involving the heat of sublimation instead of the heat of vaporization. So we can proceed next to integrate this so that we get an algebraic equation relating pressure and temperature along an equilibrium line. And we might make another approximation for that integration if we don't have too wide a temperature range over which we are carrying it out, and that is to assume that the heat of vaporization is roughly constant. Then we can pull it through the integral, and we end up with a functional form for the integrated form of this looking like this. And that'll tell us what we expect the functional form of a vapor pressure curve to look like. So when we want to fit data empirically, we're guided by the fact, the scientific fact, that it should conform to something that looks like that mathematically. And that leads us to, we can involve any number of parameters. That leads to the form that is most commonly used for what we call the Antoine equation, which is an integrated form here of the Clapeyron equation for the vapor pressure curve. And it involves three constants, A, B, and C. But in terms of those three constants, because we have three of them, that allows us to accommodate some temperature variation here of the heat of vaporization. That allows us to describe the vapor pressure curve over fairly significant temperature ranges for almost all cases. So this is also in our database that we have in the appendix of your textbook for the constants A, B, and C in Antoine's equation. And here they are, is the A, B, C for the different substances. But what's very important when you're going to use Antoine's equation is that you know exactly the form that it's going to be. That is the units for everything. You know, the units for which these A, B, and C values are valid is that we have a natural log of the vapor pressure expressed in bars. And the temperature is assumed to be in degrees K. So we should recognize that that's the only way we can use it, is to know those facts. And you should be aware that in many databases we have a different form for Antoine's equation. So we can note that here, and we can note here, let me blow it up a little bit so we can look at it. This is a very common form that you'll find in the literature. We have a common log of the vapor pressure expressed in millimeters of mercury, for example, and the temperature here in degrees C. And so the values of A, B, and C are obviously going to be different than these, because the form of Antoine's equation that we fit them into is different. And if this isn't great enough, let me move this over so we get an idea. But with the values that are tabulated, here's the temperature range of nominal validity, and you can see it's fairly broad. But actually, if you go outside it by 10 degrees or so on either side, you're still in pretty good shape. So this is pretty conservative. But if we needed to have something of greater accuracy, let's see if I can get this to go back to this size I want. I think that's it. We could have more terms added here. So you'll see databases that will have up to that, and that would be something like dt plus, say, et squared. And so you'd have another set of parameters, and that would cover. If you go as high as 5 parameters, you can cover the whole thing from the triple point up to the critical point, both of which are points on the vapor pressure curve. So everyone understand Antoine's equation and how we might use it? But it contains more information than you might think, because we can flip it around and use it to calculate the heat of vaporization. So this is just turning it around. If I turn around the Clausius-Clapyeron equation to be explicit for the heat of vaporization, I see that if I have knowledge of the vapor pressure dependence on temperature, I can use that to extract the heat of vaporization. Now, if I had direct data, I could plug them right in, but if I want to use the Antoine equation, then here it is. I'll just plug Antoine's expression for the log of the vapor pressure in, differentiate it, and here's what I get. Then I have to, of course, be careful that I use the right units and everything. B has units of temperature here, so it's RT, so energy looks looking good. So that's a quick way to get the heat of vaporization at some temperature that might be of interest. If I don't have validity of the Clausius-Clapyeron equation, say, then I may need to go back to the original Clapeyron equation. And for this, to get the heat of vaporization, I need the actual data, actual vapor pressure data, and actual data for the change in the molar volume with phase change. Now let's look at the melting point curve, because that's the same story, except now we have a different phenomenon that we're describing, that is melting going between the liquid and solid state. So here's the curve again, except the only difference is I got different subscripts here. It's solid, liquid, and the temperature here is what we call the melting point. And I can rearrange it. It's often more convenient to write it as a looks like melting point temperature as a function of pressure. And here we have it. Now it's convenient to look at, instead of these molar volumes, let's express it in terms of molar densities. So I can express this delta V SL as a difference between the reciprocals here of the molar densities. And that looks like this. So if I plug that back into my melting point curve equation, it looks like this. And that will tell us the nature of it. Now let's just for a second consider what we normally have, and that is that the density of the solid is almost always greater than the density of the liquid. The phase transition, that means that this is a positive quantity on the right, and it means that with an increase in pressure, the melting point goes up. That's what's typical. But it's not the case for water, whereas you all know the density of ice is actually a little bit less than the density of water at the melting point. And that's often used as an explanation. Well, here we go. The phase diagram would look a little bit different than for ordinary this melting point curve slopes just a little bit to the right, but for water it's going to slope a little bit to the left. And the phenomenon of the melting point actually going down with pressure is used as an explanation for the ability to skate or to have sleds slide over the snow. The idea is that the pressure that is applied onto the surface actually causes a melting locally, so that you get a water film over which the surface can glide. I think this is a bit controversial. When I did the numbers to figure it out, my answer was you need to be an 800-pound gorilla in order to have enough pressure on that to actually get the ice to melt. So there's more to it than that, although that's probably part of it. So let's summarize and look at the phase equilibrium data that we've now described, all with the help of the original Clapeyron equation. So here's our vapor pressure curve, and I've drawn a red line here schematically to indicate the region in which the Clausius-Clapyeron equation is probably valid. And we can write down the expression for in terms of the differential equation describing each of these three curves. And then I've shown how we can integrate it, and we're helped by making certain approximations when we do that. But here is the whole picture. So I think we've got that pretty well summarized. So what about volumetric properties? I haven't addressed that yet, because this diagram is a pressure and temperature diagram, so I don't explicitly tell you what the density or the molar volume is at any particular point. But I could it exists. I have data that would allow me to calculate that. So for any particular point I choose here, I would be able to, if I have complete data, state what the molar volume is. So one way of representing that information on a pressure temperature diagram would be to plot lines of constant molar volume. So those are called isochores, lines of constant volume, and if I put one in, it might look something like this. So this refers to some particular molar volume, and right away you see how it changes here drastically as I go from the liquid to the vapor phase. I have to move up the curve to go out. So these are odd looking things, but let me put a couple more on here. And these would refer to increasing molar volumes. Now you could imagine if I had a pressure temperature phase diagram and I populated it with a whole set of isochores, that I would have more or less complete information, right, for the volumetric behavior of this material. It turns out that while we can do that, it's a rather awkward way to do it. So a better way to handle it, if we're interested in that, the volumetric behavior, is to, instead of having pressure temperature phase diagrams, let's go over to pressure volume phase diagrams. So in this case, I've got pressure plotted against molar volume here, and then I have a family of curves which are each at constant temperature or isotherms. Yeah.
Before you get too far ahead, 2 slides back, there was a variable z. What was that?
This one?
And the bottom right there, change in z, superscript LV.
Talking about this?
Yep.
I have it as an equality, but I kind of wanted to make this an approximation.
Now, what is the
It
z?
isn't exact. What is delta z? Oh, sorry. We'll get to this. This is the compressibility factor.
Okay.
It's defined as PV over RT. But we'll get to that in detail. I don't know whether you've seen that yet or not in your 325. Yeah. But we're going to hit it in detail here as we get going. So it's convenient to represent our phase behavior on a pressure volume phase diagram instead. These isotherms, then we have a region representing the two-phase behavior between your gas phase and the liquid phase, where we have a finite jump here in the molar volume, as you all know. And these isotherms, this is just qualitatively characteristic of the way they look. We'll pay particular attention, they're increasing in that direction, to the one that passes through the critical point, which is now at the top of this two-phase envelope. And that, at that point, which is mathematically a point of inflection, which means that both the first and second derivatives of the critical point isotherm are going to be 0. So the first derivative and second derivative are both 0, which turns out to be a very important aspect of this that we're going to make use of as we go forward. I've just shown here a limited pressure volume phase diagram where I haven't included the solid phase, but that would be easy enough to do. I can just broaden it out, and if I have the solid phase included in that, don't take this too literally, this is qualitatively the case. Then I can identify the triple point isotherm as well, and that would be going through here, and you'll notice that this particular triple point temperature, I've got coexistence of all 3 phases. So let's try to notice some generalizations about this behavior that we can make use of. I've already noted one very important one here.
Mr. Burke, there's a question up front.
Yeah.
What was the name of the spot where the first and second derivatives are 0? Again?
At the critical point, this
That's the
isotherm
that's the critical
goes
point
through
right there.
goes through the critical point, and at the critical point, it's a point of inflection mathematically,
Okay, so
which
it's not
means that
something
the first and
else.
second derivatives are 0.
Thank you.
Yeah. So anything more? So another generalization that we need to, of course you know this, but it's important to point it out, that no matter what the substance is, if we go to a low enough pressure, it'll be an ideal gas. And so in the limit, as the pressure goes to zero, PV is equal to RT. And that means that the isotherms down here at very, very low pressures that I'm suggesting here will be described by that relationship. So those are kind of the generalizations. We have a critical point, we have ideal gas behavior at low pressure, so that gives us a good starting point for the complete description. So let's move on to calorimetric properties, which is next in the list of things that we can measure. So this is very simple in its description. We just measure the temperature rise of some substance that we know we have a certain amount of a certain reference substance. And as we add heat to it, we measure how the temperature increases. And the general definition of any heat capacity is going to be this. It's the increment of heat added over the temperature change at whatever conditions we have. And normally this is constant volume or constant pressure, although as I keep saying, we can also have other things, and we'll explore that as we get into it more. So let's consider simple compressible substances. This whole aspect, I don't want to jump too fast, but now let's take a look at what this might consist of. So simple compressible substances have an internal energy which has as its components many things, and I gave you a diagram earlier on in the course showing you various ways that these materials can possess internal energy. We can make one distinction between all of the different forms, and that is we can distinguish between energy, the sum of the energy that each of the individual molecules possesses on its own, plus the energy associated with the interaction between the molecules. Now, if I'm dealing with gases, particularly ideal gases, then this part is negligible. That is, the molecules on the average are far enough apart from one another that they don't have anything that contributes to the internal energy of the system. So if we look at the energy that can be possessed by molecules by themselves, it can be three different things. The energy here of translation, rotation, and then vibration of the various bonds that hold the atoms together in the molecule. And that's the entire story there. For ideal gases, we don't have any of these interactions, so we can write with complete correctness that gases at low pressure have negligible configurational energy, so the internal energy of an ideal gas is the sum of the internal energies of these individual molecules, which is made up of these three things. So notice that these things, we can write out what these are. This is 3/2 kT for on a molar basis. This is kT, it's our RT. 3/2 RT, I should say, and this is on a molar basis. This is R on a molar base, RT on a molar basis. And this one varies with temperature depending on